Hi, welcome to the dynamics tutorials. So in this case we have another problem with equations of motion and polar coordinates, and we're looking at the kinetics. So we have a particle that's confined within this vertical slot, the slot in purple here, and then we have an arm that's rotating counterclockwise that's moving the particle up the slot. Motion is in the vertical plane, so it means that we need to consider the force due to gravity, and it's going to be acting in the negative y direction. And then our slotted arm is at an angle of 45, and it's rotating at a constant angular velocity of 1 radian per second. So that means that theta double dot, the angular acceleration, is going to be 0. We want to find the force exerted on the particle both by the slotted arm and also by the vertical slot or vertical groove at this instant when theta is equal to 45 degrees. So as always, our first step is to figure out the free body diagram. And again, sometimes it's easier to just go ahead and draw the coordinates on the particle, and then you can transfer them down to your free body diagram. So obviously we have horizontal and vertical directions there, and then remember that the R direction is set by just an extension of R. So R would continue going in this direction, so that gives us R. If we're at 45 degrees, then that means that the angle between R and X is going to be 45 degrees. And then remember that theta, or the transverse axis, always goes perpendicular to R, but in the direction of increasing theta. So theta is going to go in this direction for that axis. Then we can transfer that down to a particle free body diagram. So there's our particle, there's our x and our y axes, there's our r and our theta axes, and then the particle is going to have a force from the guide, and it could be from either wall. So in this case I drew it acting towards the left here, but it could also act towards the right. And then we have a force from the arm that could go in either direction, so I drew it going in this direction up in the positive theta direction. But it could also come down in the negative theta direction because the arm has contact points on both sides. Now we just have to go through and kind of figure out how we can get the values before we start doing sum of forces. So the first thing that we notice in this one, we didn't even get an equation for R. So let's go back to the geometry and say, okay, if this is R between the origin and the particle, and this is 2 meters, then we could say 2 meters is equal to R cosine of theta. Then we could rearrange that so that we get R is equal to 2 meters over cosine of theta. So there's our equation for R. We can plug in 45 degrees and then we can get that value for R. Remember, with these problems, just like with the kinematics approach with polar coordinates, we're going to just fill in this table R, R dot, R double dot, theta, theta dot, theta double dot. So now R dot is a little bit complicated. I'm just going to approach it just the way that I thought was simplest, which was cosine to the -1 power. But if you wanted to use a different trig function for that and use the derivatives, you'll get the same answer in the end. You'll just be rearranging terms to get the same answer. So if you think about cosine to the -1 power, take the derivative, -1 comes out in front, then you'd have the 2 meters divided by cosine now to the -2 power. Then you have to take the derivative of the cosine of theta, so you get minus sine of theta. The derivative is with respect to time, so now you need the derivative with respect to time of theta, and that gives you that theta dot. So this is a little bit complicated here. Now go on to our second derivative, because we have 3 terms that all depend on theta. We have theta dot, sine of theta, and then cosine squared of theta. So let's take our second derivative, so we can do just the derivative of sine of theta, so that'll give us 2 meters cosine of theta divided by the cosine squared of theta that's already there, times another theta dot, and we already have a theta dot there, so it'd give us a theta dot squared. Then we'll have the derivative of cosine to the negative 2 power. That'll kick out another negative sign. It'll kick out another negative, so negative times a negative is a positive. The 2 from here will then be multiplied by the 2 that's here, and we'll get the 4. And then we'll kick out another theta dot multiplied by the theta dot that we already have there, and that'll give us a theta dot squared. And then, fortunately with this one, theta double dot was 0 because the problem said we had a constant rate of theta dot equals 1 radian per second. So we don't even have to mess with the derivative of the third term, because once we get theta double dot is 0, that'll zero out that third term. So plug that in, get that value for that, get the value for r dot, and then just write down the values for theta, theta dot, and theta double dot from the problem statement. Then, just like with the kinematics problem, we write our acceleration in the radial component and just plug in our values, and our acceleration in our theta direction or transverse direction, and then just plug in our values. Then we can do our sum of forces. So I started with sum of forces in the r direction. So we're going to have the 45, oops, sorry. Let's draw in that angle of 45 there to the theta direction. So that'll give us the component of the weight. And then we'll have nothing from FA because it only goes in the theta or transverse direction. But we'll have the NG, and there's another 45 in here. So we'll have the normal force from the guide times sine of 45, and it's going in the negative r direction, as is the weight. Then we have our mass times our acceleration in the r or radial direction, and we can solve for NG. We get a negative number, but that's okay because remember NG could have either sense. It could be going to the right or it could be going to the left. Either one is fine. Then we'll do our sum of forces in the theta direction and get that's equal to mass times a theta. And so we'll have our arm force that only goes in the theta direction, and then we'll have the theta components of NG and the theta components of the weight, and that'll equal the mass times the acceleration in the theta direction. When you carry this down, because you've already figured out the sign based on the direction in the free body diagram, and now you got a negative sign here, that means that the sense is opposite what you had in the free body diagram, so make for sure that you copy the negative sign down into the formula when you plug that in. And we get a FA then of 50.4 newtons. Thanks for watching.